says Orsa, Italy.
That's
Perfect.
good enough.
Good, good, good. Okay. Dreaming. Okay, cool. Yeah, so hey everyone, I'm Michael. This talk is going to fit in more on the sort of discussion of things we were having on Wednesday about transport maps and sampling. I want to tell you about something that we're calling stochastic interpolants, which we're trying to pitch as sort of a unifying framework between these sort of flow-based deterministic maps and the sort of recent advances in score-based diffusion that are giving people access to these models of stochastic dynamics that they use to model probability densities. So this is going to be joint work with Eric van den Eyden, Nick Boffey, and Michael Lindsay. So just quickly to say thanks to all my collaborators, but just to highlight the three of them. Right. Okay, so the topic is going to be density estimation and sampling with transport maps. You know, sort of by name, I'm more interested in the sampling part of this. The density estimation and generation from data is sort of what the machine learning community cares about. I'd like to solve the latter. This is something I've been working on with the folks in the previous slide since around 2019, primarily for applications in QCD, so trying to overcome some issues in lattice field theory. But so yeah, I want to motivate this picture and give a little background for the flow-based transport paradigm. I'm probably going to glance over some of it because we've done it a few times since Wednesday. So I'll save you guys the trouble. But I'll pitch the challenge. You know, Mary Lou was talking about this. You know, what's the best way to learn expressive and scalable transport maps? You know, if our map is not good enough, using it in any sort of Monte Carlo scheme or using it to generate samples from an empirical distribution is going to be difficult. So we want to think about, you know, what's the best way to do that. And I'm going to take some inspiration from score-based diffusion to talk about this. So they've sort of rethought a way of training these models that we can apply to flow-based transport that is going to help. So the way we're going to do this is what I've been calling and what we've been calling as a group, this stochastic interpolants paradigm. So I'm going to talk about how we can get some unbiased generative modeling through either these deterministic or stochastic dynamics. And in fact, when you look at the ODE versus the SE, there's actually a theoretical trade-off that you can write down about what you can expect from maps like this. And then, you know, with this paradigm, I'll talk a little bit about the different things you may be able to do. It's kind of more like a hammer right now with no nail, but that's why we're here. So yeah. Okay, problem setup is to estimate an unknown probability density function that I'm calling rho1, either through sample data or query access to the normalized log likelihood. We here care about the latter. Unfortunately, I'm going to talk about the former today because we collectively sort of need your help in solving the latter problem. So the pitch is that, you know, since 2012, the pace of development in generative modeling has been kind of astronomical. We've gone from modeling these black and white, you know, very pixelated digits to you know, being able to query some text command that says, draw me a picture of bears that are scientists doing chemistry experiments in a cartoon form, and you'll get something like this. And one of the interesting facts about this is a lot of the success has you know, coincided with a measure transport perspective. Many of these models are built on this notion of measure transport, you know, and that's useful for the scientific computing paradigm because usually that's what we have access to, some notion of the target density defined by the theory. So in this transport framework, we'll have some simple base density that I'll call rho0, and I want to learn a map T that pushes this base density to rho1, which is our target density that I defined before. It's going to be some sort of complicated thing where the base is usually going to be something very simple like a Gaussian. And importantly, you know, the density of rho1 can actually be defined explicitly in terms of this map by looking at a sample from rho1, looking at its inverse push back to rho0, evaluating that likelihood, and computing the change of measure that occurred under that transformation. Okay, if we want to do this parametrically, we don't actually have access to T for many problems that we care about. We need to learn a T, okay? But if T is really complicated, then this determinant is going to be very expensive and not so useful. And we want T to also be maximally unconstrained so that we can learn an expressive map and actually solve our minimization problem. We have to balance this trade-off when we're thinking about this. So historically, this problem has some of its origins in the sort of contemporary machine learning framework going back to Chen and Gopinath in this Gaussianization paper from 2000. And then Esteban Tabak and Eric, my collaborator, sort of thought about how to do this in some iterative procedure that is going to minimize some sort of cross entropy. They extended that with Turner, and then on came the neural networks around 2014, where they said, okay, if we're going to try to solve this problem, we don't want to try to do it all at once. Let's take inspiration from these earlier things where we do it in an iterative iterative procedure. We learn some iterative transports, TK, which are easier to actualize. And then we'll have those iterative transports be neural networks that have a favorable Jacobian that we can calculate to compute this change of measure. So this is work of like Laurent Din and Danilo Rezende, George Papamacarios, folks like that. And then the perspective came of saying, okay, if it was easier to do this in these incremental fashion, let's take the k equals infinity limit here and say t is actually the solution of some sort of continuous time flow. Okay. And if you do that, that determinant of this Jacobian we had to compute before becomes a trace of the instantaneous change in the velocity field that governs this continuous time flow. So I'll unpack what that means in the next slide. But people like this because it means that you can estimate this this trace, in an unbiased way in only something that scales linearly in the dimension. So maybe this is useful. And you can, it's integrable with all the neural ODE paradigms that have emerged since 2018. So just to really frame this picture, put it all up at once, we're probably primarily going to be thinking today about a flow map that I'll call XT, okay? XT is such that for some initial condition from the base density that we'll call X, at time t equals 0, it's equal to X. And then we want to, solve the ODE, which is described by some velocity field B, right? Which pushes us along these flow lines to sample from some target density, okay? So that's how we're going to realize the map. It's going to be the integration of this ODE. So the motivation for this is then to ask, at the level of the distribution, how does the intermediate density rho t that corresponds to, any time step along this path evolve? And we know that that's going to be governed by some sort of transport equation, which is just basically saying that the change of measure is conserved by this, the change in the probability density. So if rho t solves this transport equation, then we'll actually get at time t equal 1, right, to our target density rho 1. And Benamou-Bernier theory says, okay, this thing should exist under some mild conditions. And our goal now is to figure out how do we learn BT, the actual map that we will parameterize eventually to make this push forward happen. Okay, so one approach when this was originally pitched is just to do maximum likelihood estimation. Okay, so this is just the continuous time version of that change of variables formula I wrote on one of the earlier slides. But what you'll note is that if you try to do this, if BT is some neural network, right? If you try to do this, you need to be able to solve this ODE to evaluate your loss function. Okay, so the loss actually involves integrating with the ODE. And that means you need to, update the parameters of your neural network by backpropagating through an iterative solving procedure or use some sort of a joint sensitivity method that is going to save you memory, but is going to be costly in time. Moreover, there's many paths that go from rho 0 to rho 1. We're assuming that doing this maximum likelihood is choosing one for us, but maybe if we explicitly define one, we can sort of help ourselves out on this problem. So we want to ask, is there a simpler paradigm for learning this velocity field? Our dream scenario would just be that we do regression on some known velocity field. We know regression is a really well understood problem. And if there's a way for us to do this such that we can sample from the time-dependent density, rho t, anywhere on this transport between rho 0 and rho 1, and learn the velocity everywhere over that time interval, then we're in pretty good position here because that'll basically solve our problem. Okay, the issue is we don't have a fixed velocity field to regression on, and we don't actually have a way to sample from rho t to do this. So we want to ask, is there a way for us to build a connection between row 0 and row 1, our base and our target density, that allows us to get this velocity field directly and then learn it. So the pitch from this, question that I want to push forward is we can define this thing called a stochastic interpolant, okay, which relies on this object we'll call an interpolant function I. Okay? It's a function of time and both samples from the base density x0 and samples from the target density that we're trying to sample under x1. Okay, and it just has these specific conditions that at time t equals 0, this function is going to evaluate to x0, and then at time t equal 1, it's going to evaluate to x1. Really simple example is just linear interpolation, 1 minus t x0 plus t x1. Okay. But if you draw x0 and x1 from some joint density, this joint density could be simply just independently drawing x0 and independently drawing x1 from the two distributions you have sample access to, then the claim is that this interpolant IT x0, x1 is a stochastic process which actually samples this density for you. So by randomly drawing x0 and x1 according to some joint density, this gives you a way to sample from the intermediate density anywhere in the interval that we cared about. So for example, if you went from, as we had before, a Gaussian to a 3-mode mixture, these are samples from doing this by just drawing samples from row 0, drawing samples from row 1, and then doing this interpolation with stochastic pairings of x0 and x1. Okay, so that allows us to tackle one part of this. Okay, we now know how to sample a row tx, right, which maps between the two densities. To say, the goal then is to say, if we have samples, what actually is the B that does this connection? Okay. We can actually just explicitly state it. I can look at a proof if we want later, but just for time, I'll say that, if we have a row T that satisfies the transport equation I wrote before, it is a valid connection between row 0 and row 1, then B is actually given directly in form of a conditional expectation of this interpolant function. Okay, it's the conditional expectation of the time derivative of the interpolant conditioned on xt, the sample you care about here is equal to x. Okay, you can prove this with characteristic functions, or I have like a sketch of doing so in backup slides if anyone cares. But just hold on to the notion that the conditional expectation with the interpolant defines the velocity field that connects the two densities. Okay, well, this gives us a form of what BTX is, so we can plug that into our regression problem that we wanted before, but we still actually don't know how to compute this. It's sort of an abstract object at this point, right? So this doesn't fully help us, but if you note that, by definition of the conditional expectation, any integral over the rho tx that we're talking about here of this conditional expectation is actually available just by doing the expectation over row 0 and row 1 of the quantity of interest. So we don't actually have to directly compute it. It's available by taking expectation over the two endpoint densities. And if this is the case, we can just plug that fact right into the regression problem we want to do and say, in expectation over row 0 and row 1, the time derivative of this interpolant function evaluated over x0 and x1, integrated over time, is an objective function for which the minimizer is directly the velocity field that we wanted to learn. So this gives us a way to do regression, basically, to solve transport problems instead of having to simulate any path along the way. So this loss is directly estimable over row 0 and row 1. It connects any two densities, okay, which is something we'll, if we want, we can talk about with respect to how score-based diffusion works, where one of these has to be a Gaussian. We can compute the likelihood, but if we want, by simulating the ODE. And this loss is actually bounds the Wasserstein 2 between what our model is and what the target actually is. It's a really weak bound, but it's something. So then the generative model we get is we would draw a sample from either endpoint of the densities, and we would solve the ODE I had on the original page, where we push forward that sample using the velocity field. Okay, so I care about the physics problems, but if you write a paper that is sort of just about ML and you send it to an ML journal, they say, why didn't you do any of the fancy image experiments And then you spend 2 months of your life burning computer time to show them that you can do that. And in the end, you wind up getting way too deep into it. But OK, this is just some examples. So for example, if you wanted to map this 2D density, which is these weird, the two moons, to this sort of very unfriendly, sharp checkerboard density, you could see that the exact interpolant gives you a way to sample from any time in between the two, from 0 to 1. And then the map you learn by actually solving the regression problem on the other side does the same thing. OK. Yeah, exactly. In this, it might have been a cosine and a sine function that have the right boundary conditions, because there's some things you can say about Gaussian mixtures that you can preserve the variance of the intermediate density with those. But honestly, I think the linear one is the most straightforward to use. OK, yeah, so it scales to high dimensional problems quite well. But then, we could ask, if this is deterministic dynamics, is there any way for us to just extend this so that we could do something stochastic? And so there is sort of a decently straightforward step that one could make to do this. You take the interpolant you had before. If it had no Gaussian endpoint to begin with, say it was one of the moons to the checker before, there's no explicit Gaussian-like quantity in there, you append on to the interpolant a gamma tz. Okay, gamma here is some function that is 0 at time t equals 0 and 0 at time t equals 1, but is positive in between. So what this is doing is it's adding to the interpolant some sort of Gaussian stochastic mixing. Okay, so an example is just take t1 minus t square rooted. It has some relations to the Brownian bridge and the Schrodinger bridge type problems. If you do this, you can write down another statement that looks exactly like the one I made for the velocity field. Okay, earlier, the velocity field now has the original time derivative of the interpolant plus the time derivative of the extra term. We could think about just calling this whole thing the interpolant and setting the time derivative equal to that. But actually, the score of rho t is available at any time too, if you knew how to compute this, as -1 over this gamma factor times the conditional expectation of this Gaussian variable, given that xt equals x. Okay, and then it too has a regression loss based on the same properties, where you just learn the score based off of z, in expectation over the endpoints, as we talked about before. Okay, so this means we have two frameworks for doing some sort of generative modeling. We had a continuity equation. Okay, now I added this Gaussian guy, and we have a Fokker-Planck equation. Okay, just saying that we're going to be able to realize this with some stochastic dynamics rather than some deterministic ones. We would use our model of V for the ODE, right? In this sort of fashion, solve this ODE. All we want to do is learn B hat. If we want to do some sort of diffusion that's fixed between two probability densities in finite time, then we need to introduce sort of an augmentation of B that includes the score and some epsilon, which is tunable after doing any of the learning, that tells you about how much Brownian motion you want to add to the SDE that fulfills the dynamics we're talking about. Okay, so you would learn a model for B and a model for S, and then whenever you went to sample or use them as a generative model, you'd set epsilon and great. Okay, I'll glance over this just because running out of time, but you can actually ask, okay, what can I say theoretically about the ODE versus the SDE? So it turns out if you wanted to bound the KL divergence between some approximate dynamics in this continuity equation and the true one, then actually it's not enough to just minimize B hat minus B. Okay, if you want to bound the KL, you actually need to bound the scores. Okay, so the score of grad log rho and grad log rho hat need to be bounded. But if it's stochastic dynamics and we're using that augmented velocity field or drift B plus epsilon S, then it turns out that just minimizing the drifts controls the KL. That's kind of nice. You can sort of show this experimentally, that for some value of epsilon, there's actually a maximal separation between the ODE and the SDE. There's caveats, though, that I'll mention now. by talking about different interpolants that we can design, sort of in line with what you're saying about using the linear. Here are the rules. You need to meet the boundary conditions of the interpolant. And if you want the score, then some component of this interpolant needs to have some Gaussian component. You know, it could be probably exponential family, but we haven't shown that. So one example is what I'll call mirror interpolation. You have only row 1 at your disposal, okay? Your interpolant is a sample from row 1, x1, plus gamma tz, okay? So you're adding noise, and then you're removing it. The endpoints are both the target density, but if you solve this problem and you get the score, which happens to be equal to up to factors the velocity field here, then using it in the SDE we showed before allows you to resample your data set. So this guy isn't in the real data set, but by starting from some image and scaling how much noise it has, I can get a sample that's like proportionally approximate in the space of samples to that one. Okay, so higher epsilon, this flower would deviate more from the original flower. You could also regenerate your entire data set from one point. So this is a sample from the checker, and then you can run the SDE with a very high diffusion term, and for 10,000 realizations, it should fulfill the entire density. Okay, you could choose one side. This is like what score-based diffusion likes to do. And you could say, I'll take Gaussian noise and I'll push it forward to a sample from the data set. I like using the flowers. For the same initial condition, okay, we get some flower with no diffusivity, deterministic dynamics. You add a little diffusivity, you get a flower that's close to it. And as you increase the epsilon, you get a flower that's farther and farther away. Okay, so it allows you to explore your data set in some new way. The cost is, even if the SDE is provably better, the number of times you need to evaluate your network to successfully integrate these dynamics scales really badly with the SDE. So I'm not really convinced the SDE is any more useful than just using the deterministic mapping. The last thing I'll say is a sort of brief new result. There's a way to generalize this to be transport in some space defined by k densities, okay, instead of just 2. And by doing this, you can learn one object that's a map from some simplex valued parameter alpha, that's our equivalent of time, across RD to some generalized velocity that has k components that you will use in a certain way to learn a map between k densities all at once. So for example, if you had 4 Gaussian mixtures, you could ask about transport from row 1 to row 0, row 0 to row 1, row 2 to row 0, every pairing that you could have of these densities. I don't know what this is super useful for, but it's, if there's a reason you may want to define some sort of dynamics and sample anywhere, generate anywhere on the simplex from some endpoint to another, this is some way that allows you to do this. Okay, summary and outlook is what we've described as a way to build flows or diffusions between arbitrary 2 densities or k densities. And there's sort of a language that emerges from this to design new maps. We can ask about questions of what's the least costly map to generate? Is there a benefit to this computationally? But the challenge, I'd like to talk with everyone here about is this was when we had a lot of data. If you only have the likelihood function, it's unclear how to totally avoid simulating the ODE and then being stuck with the same problem we had before of this being very costly, right? And moreover, the determinant you have to compute, you want to do in a way that has low variance, so you can use it in a Monte Carlo sampler in some reasonable way. I'm not totally sure I see a way to do that currently, but it would be fun to talk about. So you can see the papers for questions about designing interpolants for OT, and there's some code here if we want to play with it. This next week, I'll be here.